We've spent some time showing that equations were true for all possible values of a variable in a trigonometric equation. Now we're going to solve equations where there are just specific values of the variable that make the equation true. One thing that we want to be cautious of is, because of the periodic nature of these trigonometric ratios, sine, cosine, tangents, etc., we need to make sure that we're including all of the coterminal angles to an angle that is our solution, so that we're addressing all of the solutions to the equation. So, for example, I told you in this paragraph that if I solve an equation and get that x equals pi over 2, I would express my final answer if it was a sine or cosine equation that I solved as pi over 2 plus 2 pi n. If we're solving a tangent equation, because the period of a tangent is 1 pi, I would write the equation. So suppose I solve a tangent equation and I get that x equals pi over 4. My answer would be rewritten as x equals pi over 4 plus pi n to indicate all of the possible solutions for that equation. Also, one more thing, since we're considering all the possible values for the variable that will make the equation true, you may remember that when we took the arc sine, the arc cosine, and the arc tangent of a value in order to find the angle in the unit circle, we only looked at a certain portion of the unit circle. We're not doing that anymore. We're looking at the entire unit circle for that x value, or that y value, or that ratio. Okay, so let's begin. In the first equation, just like in algebra, how we wanted to isolate the variable, we want to isolate the trig value when we have just the sine or the cosine or the tangent. When things are squared, that's a little bit different. So here I can isolate my sine x by subtracting 2 sine x from both sides. And I get 2 sine x equals radical 2. Divide both sides by 2. And I would have that the sine of x is radical 2 over 2. That means that x is the arc sine of radical 2 over 2. So what I'm looking for on the unit circle is anywhere on the unit circle. Again, I'm not just restricted to the right half anymore. I'm trying to find anywhere where my y value, because this is sine, where my y value is positive radical 2 over 2. And that's at x equals pi over 4 and x equals 3 pi over 4. So remember that in order to express all of the possible values for x, this is pi over 4 plus 2 pi n. Similarly, 3 pi over 4 plus 2 pi n. In example 2, this time I only have one trigonometric ratio in the equation, but it's being squared. So eventually, I would hope it makes sense, I'm going to take the square root of both sides. So I've got 3 cotangent squared of x equals 3 when I subtract the 4 from both sides. Divide both sides by 3, and I've got that the cotangent squared of x is 1. And since cotangent is the reciprocal of tangent, I'm just going to run with tangent squared of x equals 1. And when I take the square root of both sides, the tangent of x equals positive or negative 1. And so I'm looking for the values in the unit circle where the ratio of y over x is 1, or negative 1. So x equals the arc tangent of positive or negative 1. So we're looking for x and y coordinates to be the same value, not necessarily the same sign, since here positive or negative works. And that happens at pi over 4, 3 pi over 4, and then you might keep going and say 5 pi over 4 and 7 pi over 4, but remember, because the period of a tangent graph, I know we didn't graph them, but the period of the tangent is 1 pi, so I would express this as pi over 4 plus pi n, or 3 pi over 4 plus pi n. And I don't have to write 5 pi over 4, because 5 pi over 4 is just what I would get by adding a pi. So that's my solution. In example 3, my instructions are telling me, first of all, I'm going to be factoring here, and second of all, that I'm only interested in the solutions from 0 to 2 pi. So if it's not on my unit circle on my reference sheet, I'm not interested in it, which means we don't have to worry about the plus 2 pi n. Okay, so I'm going to, in this first equation, part A, I'm going to bring everything over to the left-hand side. So I'll have 2 sine, x cos x minus radical 2 cos x equals 0. And notice that they have a common factor, so I'm going to factor out the cosine of x. And when I do, I have 2 sine x minus radical 2 equals 0. And so by factoring, what I have here is 2 things being multiplied together to equal 0. And we know from way back in Algebra 1 that if I have 2 things being multiplied together to equal 0, then one of them must equal 0. So either cosine x equals 0, or 2 sine x minus radical 2 equals 0. So for the first equation, I'd be looking on my unit circle for any x-coordinates of 0, and that is at pi over 2 and 3 pi over 2. For the other equation, I've got a little bit of solving to do. So I add radical 2 to both sides and divide by 2, and I've got sine x equals radical 2 over 2. And so x is the angle where I find radical 2 over 2 as the y-coordinate. That happens in 2 places, pi over 4 and 3 pi over 4. And so these are my solutions. You might want to pause your video at this time so you can finish jotting down anything you need from this screen, since I'm going to have to erase it to make room for part B. In part B, I have cosine squareds, cosines, and numbers. And so think back to your algebra. If there were x squareds and x's and numbers, then we probably ended up factoring it out like a trinomial. And that's what's going to happen here. But it's going to be pretty unattractive. So let's bring everything over to the left-hand side, and I'll have 4 cosine squared of x plus 2 cosine x minus 2 radical 2 cosine x minus radical 2 equals 0. And so when I factor this out into 2 binomials, think back to your algebra. This is a result of my last spots in my 2 parentheses. Well, how am I going to get that radical 2? With a radical 2 and a 1. And that 4x squared, or 4 cosine squared of x, one possibility might be 2 cos x and 2 cos x. And if you kind of visualize foiling this out without taking into consideration positive or negative, let's just look at 2 cos x times 2 cos x. There's my 4 cosine squared of x. 2 cos x times 1 gives me a 2 cos x. 2 cos x times radical 2 gives me 2 radical 2 cos x. And then radical 2 times 1. Okay, so all of my terms are going to show up there. I just need to make sure that my signs are correct. Since this term is negative, I want the radical 2 to be negative. And so now I've got my 2 binomials that I'm going to set equal to 0. 2 cosine x minus radical 2 equals 0, or 2 cosine x plus 1 equals 0. In the first equation, solving for x, I add radical 2 to both sides and then divide by 2. So I have cosine x equals radical 2 over 2. In the second equation, I subtract 1 and then divide by 2. So I have cosine x equals negative 1/2. And so what I'm looking for in my unit circle is anywhere I see either of those two values as the x coordinate. Again, the reason why it's the x coordinate is because this is the cosine. So on my unit circle, radical 2 over 2 shows up in the x coordinate at pi over 4, and at 7 pi over 4, it shows up as an x coordinate of negative 1/2 at 2 pi over 3, and 4 pi over 3. In this example, I kind of copied and pasted some of this out of the textbook, and I apologize that I neglected to copy and paste that in the original problem, the original initial velocity, or initial speed, excuse me, was 30 miles per second. And that kind of pops up in part B of this problem. So in part A, I am changing the initial speed, that v sub 0, to 35, and I'm trying to find out at what angle I need to hit this ball so that I'm getting to the fence, which is 90.5 meters away. So 90.5, I plug in for D. V sub 0 is 35, which is being squared, times the sine of 2 theta over 9.8. So I'm solving for that theta, which means I need to get the trig ratio by itself. Start by multiplying both sides by that 9.8. I've got 90.5 times 9.8. And that's 886.9 equal to 35 squared is 1225 times the sine of 2 theta. Divide the 1225 from both sides. And 0.724 equals the sine of 2 theta. So then 2 theta will equal the arc sine of 0.724. Okay, so what is the arc sine of that 0.724? That is 46.4. And so at this point, I want to call your attention to the fact that in previous examples, for example, here, when we took the arc sine of something, we ended up with two possible values from 0 to 180 degrees. Remember, 0 to pi is equivalent to 0 to 180 degrees. So in our calculator is spitting back degree measures, not radian measures. But I bring this to your attention so that you realize that in the span of 0 to 180, there are two angles that have that 0.724 as its sine. Okay, so the way that I find the other angle is by taking 180 minus that 46.4. Okay, so when I do that, I've got 133.6, also equal to 2 pi. And when I divide by 2 in both of those equations, I end up with one of my possible angles being 23.2, and the other possible angle being 66.7 degrees. So both of these angles will launch the ball at if my initial speed is 35 meters per second, will launch the ball to the fence, which is 90.5 meters away. In part B, same kind of problem. This time I'm trying to find the angles, the launch angles that would get the ball to the fence if the fence was only 80 meters away. So in part B, again, it's 80 meters this time, equal to, and I'm keeping the initial speed the same, the one that they gave me in the book that I forgot to copy over, so that's 30. So 80 equals 30 squared times the sine of 2 theta over 9.8. And then we solve the equation in the same manner. Okay, so 80 times 9.8 is 784, equal to 900 sine of 2 theta. Divide the 784 by 900, and I've got 0.871 repeating, equal to sine of 2 theta. 2 theta will equal the arc sine of that 0.871 repeating. And so that is 60.6. But again, remember, there's another angle that also has a sine of 0.871 repeating. And it is equivalent to, so 2 pi could also equal 180 minus 60.6, which is 119.4. And so I solve for theta in both of these equations. I get 59.7 degrees, or 30.3